Welcome to Spring LIB.
Okay, so in this problem, we are trying to determine the loss of electric potential energy between two situations where a proton and electron are near each other, like this, electron, proton, and the proton is moving towards the electron. So this is a distance here. We'll call this charge 1, Q1, and this charge 2, Q2, and this is the distance between them, R1, 2. So we can write the change in potential energy as big delta U, which is just the potential energy at the final position, B, minus the potential energy at the original position, A. And so we know from the problem statement that RA, this R12 at situation A is 0.11 nanometers, and RB, the final position, is 0.1 nanometers because the proton has moved closer. Okay, so first we need to look up the equation for electric potential energy, U, which is just 1 over 4 times pi times the constant epsilon naught times Q1 times Q2 divided by the distance between them, R12. Okay, so let's save our equations over here. And let's start plugging in. So we are solving for delta U, which equals UB first. So let's write that, 1 over 4 pi epsilon naught. Q1 is our electron. So we know that that's the charge of an electron, Q sub E, times the charge of the proton, which is just, the opposite of the charge of an electron. So that's minus QE, divided by the distance in the final distance, RB, so that's 0.1. Well, let's keep using symbols for now. Okay. Let's write RB. And then we are subtracting the potential energy at position A, where we have the same charges involved, divided by our new distance, our old distance rather, RA. All right, let's simplify this. We can take out our 1 over 4 pi epsilon naught. We can also multiply this times minus QE squared, since that's the same in both situations. And then we have a 1 over RB minus 1 over RA. Okay. So now we can plug in our constants. So we have a 1 over 4 times pi, which we can round to 3.14. You look up in the back of our book, our epsilon naught, that's 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. Okay, times, we have a minus sign here. Charge of an electron, we can also look up, that's 1.6 times 10 to the minus 19 coulombs squared. And we have inside our parentheses multiplied by the rest of that. So that's 1 over, let's change these to meters to match the rest of our units. So RB is 0.1 nanometers. So the 0.1 times 10 to the minus 9 for nano meters minus 1 over 0.11. This is RA times 10 to the minus 9 meters. Okay, so let's plug in all of this math into our calculator. And what we get is 2.09 times 10 to the minus 19. And let's look at our units here. So we have, let's make this clearer. This is all under our denominator. So this coulomb squared gets canceled out with the coulomb squared up here. So we don't have any coulombs. This gets flipped because it's on the bottom. So that's newtons times meters squared on the top. And then we have a meters to the minus 1 over here. But we know that this just equals meters to the plus 1. So meters. So this is equal to 2.09 times 10 to the minus 19 Newton meters. But this unit we know better as joules. But the question is asking us what the loss of energy is. There's also a minus sign here. Let's not forget that. We have that from the charge of the electron here. The question is asking us for the loss in potential energy. That's why we have a negative here. So it's really just asking us for the magnitude of this problem. So the last thing we have to do is convert joules to electron volts. So you can write 2.09 times 10 to the minus 19, and we need our conversion factor from joules to, from joules to electron volts. So we have our current answer in joules times our conversion factor. So we know 1 electron volt is equal to, we can multiply anything by 1.6 times 10 to the minus 19 joules. Cancel out our joules, and what we get is minus 19. These also get canceled out, 10 to the minus 19. So it's just 2.09 divided by 1.6, which gives us a minus 1.3 electron volts. The question's asking us for how much energy is lost. So we really just need the value, which is 1.3 electron volts.